semester, and I wanted to use this opportunity to share what type of research I'm doing and what could we do together. That's a good opportunity. So here's the content of my presentation. First, I will have a quick presentation of my curriculum, then research interests, and then ideas I had of what we could do together, but this is really open. I mean, it's not a closed list. So my curriculum, I have the engineering degree from the bottom, from École des Mines de Paris. No. And so it is basically Master of Science in engineering with no specialties, and I do some paleoclimatology, geotechnics, mechanics, and everything you want. Then I went to work in the US for 1 year on a geotechnical repair work of a dam in Kentucky. I've been had the chance to do my PhD with Luc Dormieux and Frédéric Scott-Chilas in École des Ponts et Chaussées and École Centrale Lille. So Ponts et Chaussées is in Paris and Lille is in the north of France. And then I stayed for 1 additional year as a teaching and research assistant in Lille. And for 10 years now, I'm assistant professor at Nantes Université. So I do my teaching activities at the civil engineering department of Polytech Nantes. Polytech Nantes is an engineering school, which is a subset of Nantes University. And I'm a researcher at the Institut de Recherche en Génie Civil et Mécanique, so the GEM lab. So why I'm here? So as faculty members in France, we can have a 6 month or 1 year sabbatical leave on a regular basis, either for pedagogy or for research. So I'm here for research. So I had some administrative tasks for more than 1 year now, so I'm paid by Nantes, and I'm here from February to, say, summer of this year. So why did I choose here? So I saw that we have mutual research interests related to micromechanics or in general, civil engineering materials and heterogeneous materials. And then there is this expertise of CTU on this Fourier accelerated numerical solvers around the group of Jan Zeman. And then I have my family is partly Czech, so I have personal interest of coming here. That was an additional motivation. So for the research I do, so I concentrate on the multiscale modeling of heterogeneous media and often porous media, I would say. So the idea is that when we solve some boundary value problem for a structure at the microscopic scale, we use a constitutive model, which is actually some average response of what are the constituents of this material. So for a mechanical problem, you would have the stress and the strain at the macroscopic scale here with capital letters that would you use to solve your problem, and their property stem actually from microscopic features where you have heterogeneous strain stress response. So depending on whether you are within a grain or in a pore or any type of heterogeneous material, you will have a different response. So one of my activities is to determine this homogenized stress response from the microstructure information and the information about the local stress strain response of each of the constituents. And for doing so, we use multiscale methods or micromechanics, and we have to assume that at any point of the macroscopic level, we can define some relative representative volume element, which is much smaller than the fluctuations of the fields at this scale, and which is much larger than the sizes of the heterogeneity at the microscopic scale, which is a usual requirement, but sometimes it is not met. And so that is for mechanics. And as you can see, we have the same type of constitutive equations at the microscopic and the macroscopic level. But something I'm really interested in as well is the flow in porous media. And for flow in porous media, it's the same picture, but now we don't have the same structure of the field equations. So at the macroscopic level, say we have some porous medium and we have a flow through that porous medium at a slow rate of flow. That could be described by Darcy's law, which linearly relates the filtration velocity or the macroscopic velocity here to the macroscopic pressure gradients through some permeability. Okay, and if you zoom in at the microscopic scale, what you see is is pores and solids. And within the pores, the flow is not described by Darcy law, but by Stokes equation, which is very different. And now the pressure gradient is balanced by the Laplacian of the velocity and not the velocity. So we have to adapt techniques which are used for micromechanics to this set of problems, and that was part of my research in the team last years. So to compute the homogeneous properties from the microscopic scale, we have either full field homogenization, which would be to solve a boundary value problem on a representative volume element using your favorite method, numerical method, or you could do some what's called mean field homogenization, in which you would try to estimate the microscopic response based on reasonable assumptions and simplifications. So either you can compute rigorous bounds to bound effective properties by above and by below, or you could do some estimates, so which are based usually on the so-called HLB inclusion problem. So just to illustrate a bit this, I concentrate mostly on these fast Fourier transform-based numerical methods, and I do a bit of this rigorous bound stuff, and mostly the HLB-based scheme. So now I spent 15 years on doing that for adapting it for permeability, and my PhD supervisor told me the more time you spend to do something, the least time you should spend on presenting it. So I will try to present it in 2 minutes. Okay, but that's 15 years of work. So for the numerical thing, the idea is you would build some representative volume element. Either you use microtomography of a real sample, or you do some numerical specimen, and then you solve the field equations you have. So for the fluid flow, for example, I've adapted these fast Fourier transform-based methods. And so we generate some sample, we discretize it on a regular grid, which is like a 3D picture with pixels in 3D. And then we solve that problem. So the grids can be really big, like I had some computation with a 1 billion voxel. So it's difficult for a traditional finite elements, I would say. And then we compute the homogeneous property. So there are some about how fine should be the grid to be accurate enough, and how large should be the specimen as compared to the size of the constituents to be representative enough. And I've addressed also these points in these articles. Then for the part about the rigorous bounds, so instead of solving this whole problem using extensive numerical means, I've tried to estimate the permeability here by using reduced microstructural information. So not the whole RBE, but just some information. So one primary information will be the porosity, and we could add either higher order information, such as endpoint correlation functions, which are spatial correlation functions, which gives you statistical information. So for example, 2-point correlation function of the fluid domain here could be what is the probability of finding 2 points x and x plus r both in the pore phase, given that they are separated by r, which is fixed, but x is moving everywhere in the microstructure. And then we do that for third order information, so 3 points. And then for permeability, as opposed to what is done in elasticity, we need additional information, which is what is the probability that 1 point is the fluid, second point is on the solid fluid interface, third point is also on the solid fluid interface. And it turns out that with very involved statistical information, which is not so easy to compute, you have a bound which is not so nice. You give a lot of effort, and the result is not as nice as what you have for elasticity. So it's much more harder to upscale permeability than elasticity. So now about the HLB-based scheme. So I tried for quite a while to adapt what we have in linear elasticity or mechanics to this context of permeability, the difficulty being that we do not have the same field equations at the microscopic scale and the macroscopic scale. And the key turned out to be that we use some effective medium, which interpolates between Stokes equation and Darcy equations, which is called Brinkman equations. And the ideas would be, for example, to represent that type of microstructure with solid grains in gray and pore phase. So you would use some representative inclusions or morphological patterns, maybe a sphere for the solid immersed in the effective medium, a sphere or a cylinder for the fluid immersed in some effective medium, And then you do some averages based on the solution to these much simpler individual problems. Okay? And from that, you can get, in some situations, very good estimates to what you have from full field simulations. But now, instead of spending 1 hour doing computation, you have 1 millisecond. Then I worked also on the homogenization of yield strength, so in the context of perfect plasticity. So the idea is when you have a heterogeneous microstructure, which is of the faces having their own local strength domain. So maybe you have more ductile parts and some parts which are less strong. You would describe at the microscopic point each strength domain by some j of x function, where x is the position. And you could have a dual representation of this domain by setting, if I give some direction of loading epsilon dot, which is the plastic strain rate, what would be the maximum plastic power I can dissipate. So that is called the support function of that domain. And it turns out that this support function is a plastic potential. So if you have a direction epsilon dot and you derive this plastic potential, you would have the point sigma in red, which is at the boundary of this interface in the direction which is as normal epsilon dot. So now at the macroscopic level, we want to find what is the homogenized strength domain, and you can define it as follows. So macroscopic stress would be in the homogenized domain. If we can find a microscopic stress field which fulfills all the static conditions, divergence sigma is equal to something, and the average stress is the macroscopic stress. And also at each point of the domain, the local stress is within the local yield strength. So obviously you can define also a support function of that domain. And it turns out that this support function can be found as a minimization problem of the total plastic power dissipated within the microstructure. So it's much like a very nonlinear elasticity. And we can solve that. And once we solve it, we can describe the boundary of that domain using these techniques. But you have to solve a very nonlinear problem. So we do the two things, either this numerical FFT-based thing or analytical estimates. So for two examples, one is this one. I have a microstructure with maybe metallic parts, which are from minus perfect plasticity, and then you have porosity. So you would solve the problem, nonlinear problem on that using some FFT-based techniques, and you can have the local support function on plastic flow dissipation. Then from that, if you load in all possible directions, you can reconstruct the boundary of the homogenized strength domain. And it turns out that because of the presence of force, the macroscopic strength is much lower than the one of the grains, of course. And you can see also emergence of the third invariant of the stress effect. So if you cut this pentatoid by some plane which is orthogonal to the direction of the spherical stresses, you will see that you do not have a circle, but some shape which has a pattern which is related to the load angle of the third invariance. And now if you slice this in the direction of this spherical strain in abscissa and deviatory strain in ordinates, then you can see that depending on the angle of your slice, you have some effect, which is this. All right. So an additional slide I added in is we can do this also with the analytical estimates. So one thing we try to do in my thesis is when you have a granular material with some grains, which you could assume that they are very resistant as compared to the interfaces between the grains, and you would describe the response at the interface between the grains by a Morph-Coulomb criterion with two parameters, the cohesion and the friction angle, right? And then we would homogenize this using a self-consistent scheme, and by having two inclusion problems, one for the pores and one for the grains surrounded by an imperfect interface, precisely to account for this friction law at the contact. And so you do some nonlinear homogenization techniques, and in the end, you can compute what is the microscopic yield strength. Here, plotted abscissa the mean stress, and ordinate is the derivative stress, and then in the depth, you have the porosity, right? So the much porosity you have, the smaller is your strength domain, of course. So now if you were to use this model and you were to load from some stress path, like in a triaxial test, you would go on a straight line like this. So when you reach the yield limit, if you reach it towards compressive state, you would decrease porosity, and then you would have hardening. But if you have a stress state which is this way, you would reach the limit in the part where you have porosity increase, and you could have softening. Well, usually we're mostly into this hardening part, and the story starts when I have hardening, I will increase the shape here and the limit till I reach the critical state line, and there the porosity no longer evolves, and you reach the free plastic flow region. So this is very analog to the Kahn-Clay model, and we have only two parameters, these more Coulomb parameters. Now, since I'm assistant professor at the GM laboratory, I've been working a lot on concrete. So concrete is a really heterogeneous material, which is studied a lot in our laboratory. And you have heterogeneities ranging from the centimeters, like gravels, millimeters, the sand, micrometer would be the hydrates and the biggest unhydrated clinker core. And if you zoom in that cement paste, you would see hydrates which have sizes which can range from the micrometer to a few nanometers. Okay. So usually to describe this, people use a cascade of multiscale techniques, and with many scales involved, and you have many scales transitions. So we did that, and having some project related to the resistance of concrete to chloride penetration to prevent the corrosion of steel rebars. So what we wanted to do is that there are many things in the literature that do that already, but they either do it for diffusion or they do it for elastic or mechanical properties. But I wanted to have a model that can do both at the same time. Okay, and for that you need a microstructure description that is accurate enough. It's not so easy to describe the microstructure of a cement paste, and just to zoom on cement paste, which controls the response of concrete, we've already had to put three levels or three scales, size scales. So here's a micrometer on the right and nanometer on the left. And so you have to bring some information to your model, which is what is the, say, Young modulus of each of the constituents. And you have literature data on that. Give some information about the shape that you use to represent the constituents, either a sphere or some elongated or flat particles. And then what are the volume fractions of each of the constituents, which you can have from a hydration model, hydration of cement. And from that, we were able to see that for mature cement paste, which have been hydrated for more than 1 year, we can account for the decrease in Young modulus you would have when you increase the water to cement ratio at the mixing time, because you have more porosity. And in the meantime, when you increase the water to cement ratio, you have more porosity, and your diffusion coefficient, increases about 1 to 2 order of magnitudes. What we can see is that the coefficient of diffusion, for the size in the cement paste is by 3 order of magnitudes smaller than the one of ions in free water. And that is because of a dilution effect, but also because of interaction of ions with the surface of the CSH gels here, which are nanometric scale ports with a high surface. So using that and combining it with the hydration model to see the evolution of the volume fractions of the constituents with times. So as time hydrates, you would consume water, reduce porosity, and produce new hydrates. So your Young modulus would increase and your diffusion coefficient would drop. Okay. Some other concrete pathology which are studied in the lab is delayed intringite formation, which is a pathology you have in concrete which has been exposed to early elevated temperature. If you do a big pillar of a bridge, okay, due to the self-healing of concrete, it will heat up a lot. And then that would release, break some the heterogite, which is one of the hydrate of concrete, which is created early, release sulfate ions within the CSH. And then at later age, if you have a lixiviation of your concrete by exposure to water, you will reduce the pH of concrete. And at some point, the sulfate ions can recreate again heterogite, but in a hardened cement base. And that would create crystallization pressure that leads to the swelling of the cement paste. But because concrete is heterogeneous and the gravels and the sand, they do not swell, you have incompatibility of the deformation. So you have microcracking. Okay? So we try to model a bit of that by introducing microcracks and doing that with the mean field homogenization techniques. Right? And so here we had some, I would say, poroelastic setting. So it's purely elastic with some free strain, which is brought by this epsilon star, which is brought by this expansion. And you can compute what is the potential energy as a function of the loading parameter, which has the microscopic strain and this free expansion, and this crack density parameter. And that involves some coupled terms like in the poroelasticity or thermoelasticity. And then we would propagate damage or increase the microcrack density based on the driving force, which is the derivative of this potential energy with respect to this density of microcracks. So independent on this damage criterion here, what we can see from homogenization is that as you will increase the crack density parameter, okay, you will reduce the Young modulus of your thing, and similarly for all the coupling terms in the poroelastic formulation. Then the diffusion coefficient will increase in turn, yeah, which will accelerate the lixivation and will in turn increase the free expansion. And if we compare that to some experimental results we have in the lab, the increase in diffusion coefficient as a function of the apparent mechanical damage, we have this would be like a damage parameter in the classical, let's say, Lemaitre-Chaboch formulation. Then we retrieve trains which we have in the lab. And then we try to compare what we have measurements on the the microscopic expansion of mortars exposed to this delayed intrinsic formation as a function of the loss of the Young modulus we measure in the lab. And so with that model, we could, okay, find some damage evolution law that allowed us to reproduce that. But there is a major problem, is that you have a large expansion. So if you have a purely elastic model, you will have very large internal stresses, which are not possible. Okay, so this model is not good. We have to add creep or maybe plasticity, and I would be happy to have some help on that. Then, okay, I will not go into the details, but there's a list of some projects I've been involved into. And what is important for you is this, okay? So this is gacha, French gacha. And so you can get money out of it. And I would say that there are some types of projects which are either dedicated to young investigators or some types of project related to collaboration with companies. But there is also a type which is related to collaboration with international other laboratories. And we could get amounts of money which are, okay, a few hundreds of kilo euros. So say a couple of PhDs. And so that is something we could think about. And usually you have to send something in October, a first version of 4 pages. And then if it gets accepted, the second round will be in February, 20 pages. And then you have the result in July.
So, very nice.
Because not exactly the same time as Gacha, it could be nice to recycle some projects.
Yeah, so related to that, actually, I recently money which are funded by CRNS.
Yeah.
It was on different topics, but this is also something you can consider.
Yeah, sure. I mean, this is one of the agencies, but we have also the CRNS, or the Academy of Science. We have also some local, regional.
No, this is fine. I just meant that, this was related to some optimal control, whatever. But whether we can think about starting something similar with your lab, for instance.
I believe I don't know exactly this. There are many types of scenarios here.
Yeah, I know. I have the proposal. I think I can then. Yeah.
Okay, so
Okay, nice.
we can have a look at this.
But you are eligible as a the group.
So I'm not the CNRS researcher, but my lab is affiliated with
Yeah.
CNRS. Maybe there could be some possibilities. Okay, and so some more recent projects which are on the, so again, diffusion in concrete, but then we go here at the atomistic scale to see what is this interface effect on the nanoscale pulse using molecular dynamics. And we have already very nice results about that. Then we have an ongoing project on the very thin metallic sheets, which have a reduction of their yield strength because they are so thin. And it's because you have only a few crystals of in the thickness of the sheet, and which does not really, you have a leak of the dislocation density, and then can be healed by depositing a very thin layer of very thin metallic crystals on the top of this thing. But to model it properly, we need some gradient crystal plasticity model. So we're trying to do that with this fast Fourier transform. And then I will be involved in a project also related to the hygrothermal properties of raw earth with the composites with the biofibers, which are used in traditional building. So, but what we could do together? So I'm here, I contacted Jan Zeman to work on this FFT-based method, and usually they are designed to work traditionally on a uniform discretization grid. And recently it has been introduced that you can transform that grid, okay, and actually work on a grid which is transformed and define your physical problem in that transformed grid, where you have maybe a higher density of mesh points of interest, and then pull back this problem to the computational domain with a regular grid by doing things which we are used to do in the large scale. Okay? But now the transformation here for this mapping is not related to the physical displacement. So if you have a linear elastic thing on the physical domain, then in the computational domain, it will stay linear. So it is a nice feature. I will not go into this, and it's wrong. So what we are trying to do is now if we move only some, if we have some heterogeneous media in which you have heterogeneities which have shape that do not fit this regular grid. And so if you discretize it without too much care, you will introduce some oscillations near the boundary of the constituents. So what we're trying to do is to move the nodes near the boundary to have conformal elements. And that combines very well to what is done here about this FEM discretization combined with this FFT-based homogenization. So what the cost to pay when you do that, so maybe you have some stiffness here, stiffness 2, stiffness 1. If you bend the elements in the computational grid, you will have now more than 2 stiffnesses. You will have a stiffness field which is heterogeneous and particularly around the inclusions. But we can solve that with these methods that are dedicated to heterogeneous media. So a few results I had recently. So I compare what we do traditionally on a uniform grid on the left to what we could do if we move the knob on the right to some exact solution. So this is in conduction. The core here is insulating. The shell around it is very conductive, and it is immersed in some media which is neutral with respect to this composite inclusion. So you have no temperature gradients in the matrix around it, but you have very large gradients within the shell. And if you do that with a traditional FFT-based method on uniform grid using traditional trigonometric discretization, for a bad resolution, as we have here, you will get lots of oscillation and very bad results. If you use the FEM integration and discretization, you improve a bit. Okay, this is a very low resolution. So if you increase the resolution, you will converge to the solution, obviously. But if you have a very large domain, you cannot have a very good resolution on each of the constituents. So usually we're in this case. So now if I move the dots and I use the traditional trigonometric Fourier basis, I still have the problems because this movement is too high frequency for the trigonometric basis. So it has trouble to capture it. Where if you do it with the FEM discretization, you retrieve almost the exact solution. Okay, so which is the traditional behavior we have in FEM, but the resolution is accelerated by the fast Fourier transform. And instead of having, say, 500 iterations, you would have 40. So yeah, some potential applications. I'm still working on this yield design homogenization, and it's a pretty tough topic because this plastic potential is really nonlinear and it is not strongly convex, and it has in the regions where you do not have this plastic strain, you would have like an infinite stiffness, tangent stiffness, second stiffness, sorry. So also you have non-unicity of the solution for the strain, but the stress is unique. And so depending on which type of discretization you use, here on the different columns, you have different types of discretization, your response can be very different. And also, if you change the reference medium of the FFT-based method, you would change also the response. So there is much investigation to do with that. And that's my letter to Santa Claus. If you could help me on these types of problem where we want to have a regularization of damage to see crack propagation and so on. I know nothing about that, so I think you have really good skills here. So I would be happy to have any help on that. And finally, something I really like to do on a personal point of view is to be able, when I have a 3D picture of the porous medium, usually in real life, in a concrete, you would have, say, gas and liquid within the pores, not only liquid or not only gas. Okay, so where is the interface between the two? And that has a huge influence on the mechanical response and all the transport properties. So I would like to be able to see where is this liquid gas interface. And for that, we could use, for example, Canhilliard type formulation when you have a smeared interface energy with some regularization parameter eta. And so I did some experiments on the periodic domain where you have a square solid and then it repeats periodically. And here you have the pore. And then as you increase the water content, first you will have drops, then these drops will form bounds. And then if you have too much water, these bounds will collapse and you have only some air bubbles in the end. So that's something I would like to do. I've been a bit too long, sorry about that. And now, well, it could be a good discussion, I mean.
Yeah, well, as you wish. So thank you for your presentation, Francois, once more. It is as impressive as last time, perhaps even a bit more. So, now you see that I was serious that it would be nice to keep him, Francois, here for a bit longer because he knows a lot of stuff. So any questions, remarks?
Have you done anything in 3D? Because the images are in 2D, but probably have tried also the 3D problems or?
Oh yeah. Well, depends on which.
I mean, the images were shown in.
Well, usually it's
then.
I mean, this. Okay, this.
Okay, here, yes, sure.
And this is I make a 2D plot, but this is 3D actually. Most of it is 3D, I would say. Mm-hmm. This is also 3D. It's just a way to draw it. Just some of the later problems at the very end, so we're 2D, which was just to try that method before. And now we can do with this FFT-based method, we can go 3D simulations on a very high scale. And now we have access to the supercomputer in Mount, so we can even do
this high scale. Adaptivity is also developed for 3D, right?
Yeah.
Yeah, but this is what we are working.
Yeah, I started this in December.
Unfortunately, we are not the only ones, obviously.
Yeah. So I would say a hot topic in that domain.
Yeah,
yes.
Thank you very nice for your talk. My question is about porosity and microcracking, which probably are inside any paste. And you were talking about permeability and also ion diffusion, etc. But what is your opinion on the role of microcracks inside? Because you haven't probably touched it too much. This problem.
Except what I showed.
People were measuring that. I know in parallel, and they were showing actually that the effect is quite strong of microcracks that start to connect different parts.
Exactly. Yeah, that is what we saw here, and in our lab. So for the experimental part, we have very skilled researchers there that have done experiments on cracked concrete, either for permeability or for diffusion coefficient. And so, if you're interested in that, I could refer to their experimental work.
Okay.
Good to have the experimental results first, and then for the modeling, yes, for sure. I think they play a predominant role. Actually, during my PhD thesis, I was doing a lot of permeability measurements on not on concrete, but on mud rocks, so argillite or these rocks you would have in underground gas storage. And some of my samples were cracked, but really strongly cracked. And here in the lab in Lille, they have these fantastic devices where you could do permeability measurements under confining pressure up to 60 megapascals. Okay. And what I was seeing is that as I increased the confining pressure on these cracked specimens, I was able to see changes in permeability by 4 to 5 order of magnitudes.
If you put it the other way, if you introduce cracks, you drop it 4 orders of magnitude down.
Yeah, so that was for mud rocks, and these are even less permeable than concrete. So if you introduce cracks, you will have a gigantic effect. For concrete, for sure, we should be very careful about measurements of permeability. So either you do measurement of permeability with water, okay, which is very slow, very hard to have. Either some people, they dry the concrete and then they do gas permeability measurement, but then you induce cracking.
Yeah.
So maybe it would be good to change the confining pressure to see how it does evolve with confinement to assess the presence or no of cracks.
Okay, so we can talk a little bit later about that because
it's a very
in your experiment.
Complicated things because all the diffusion coefficient measurements we have also, we are not sure really what is the state of the concrete during the measurement. Does it has microcracking or not? It's a never-ending question.
And the second question, you were talking about this DEF. Were you able to reproduce macroscopic expansion based on some lab data in terms of, I don't know, chemical phases and what is happening in the microstructure? Because we are having actually a pretty big issues with that, even introducing, different creep as you were talking that this is proposed, but still we are unable actually to capture it. There are some mechanisms that we don't know how they should actually work. So I'm just asking, maybe you are successful with some simple model in that.
No. It's very complicated, and we stopped here. We wanted to go much further than this, but so we found a chemical model that was in the literature that was by Alain Cellier, Stéphane Multon in Toulouse, that was able to predict what could be the amount of yttriumite which is formed. So we have the volume of formed yttriumite. Then it turns out that some of that yttriumite will actually cause the crystallization pressure, but that would be only nanometric pores. Then some of the ions, they would migrate to larger pores, but it can create crystals which do not have a high crystallization pressure, and these do not contribute to expansion. So it's very complicated and intricate. You have chemistry, you have crystallization pressures, you have evolving concrete, you have creep, you have everything in this problem is a pure nightmare.
Actually trying to couple those geochemical models exactly as you are talking, but we ended up that we don't know actually what is the dependence between crystallization pressure and something else, because it seems that it slows down significantly if by expansion actually, that you drop down this expansion if you start exerting some hydrostatic pressure on that. And that's very end because you don't have data for that. So you can make a lot of hypotheses, but still trying for 3 years and still no success.
Well, I'm happy to see I'm the only one who has trouble with that. Yeah. So I saw some model in literature, but I'm not really convinced. Take a lot of mechanisms, but they make some pretty strong assumptions.
Okay. So there is still a lot of, I would say, potential to elaborate a little bit on that.
Yeah. I mean, that would be for other types of pathology and also for drying shrinkage or hydration shrinkage that could be. as you mentioned, that would be very interesting to investigate further this.
Okay, thanks.
Thanks for your excellent presentation. I have two questions. In your 3D model, you mentioned that you have millions of elements. I'm wondering what is the computation cost? Yeah.
Okay, if you have 1 billion elements, and say you have to store.
In your slide, you have present a 3D model.
Yeah. So yeah, I said we can have up to 1 billion.
1 billion. Okay.
Yeah, 1 billion. So I don't know which slide it was anyway. So 1 billion element. If you have to store a single scalar quantity in each single element, means you have to store 1 billion scalars, and that is 8 gigabytes in RAM. Okay. So now if you want to store a strain, you have a small strain, you have 6 times 8 gigabytes. Okay, that gives you an idea of. So the good thing is we do not have to store the stiffness matrix.
Okay.
There's no stiffness. It's computed on the fly. So yeah, and for say that simulation of fluid flow through 1 billion elements, that took about a couple of hours on a good desktop computer, not a
only a couple of hours.
Yeah, it was not on a supercomputer; it was on a desktop computer.
Yeah.
And this is the selling point of these methods, that you can do that.
My second question is about home generation. You mentioned that you consider the plasticity and damage, and basically, in my opinion, they are localized. But if you want to use a home generation method for this kind of phenomenon, I think they have some conflict, because for damage and plasticity is localized, but you want to home generate.
Yeah, I think you need to see it maybe in a multiscale fashion. When you have the propagation of a crack, this damage process, which you have maybe diffuse microcracking going on there, and maybe you could use that part. And then about the last thing, very perspective I showed here, I think, yeah, obviously at some point, if you have a localization, you have a through crack, you escape from this assumption of scale separations. But still, you could use that numerical method, not on the homogenization purpose, but just for computing a structural response on a heterogeneous sample. And you could avoid this periodic boundary effect that forces the crack to end up here where it started at the beginning, by putting a layer of pixels here, which is air, they have no stiffness. Then you have free edges, and then you can avoid this. Use this method, which was dedicated to homogenization, but for other purposes.
Or Ivana is considering some options how to change the boundary condition.
Oh, that would be very nice. Yeah, there are some papers in that.
From slightly different perspective that I do believe. So any other questions, remarks?
If I may. I was wondering, you were showing some mean field or HLB-based solutions using two-point probability function.
Oh no, that was not HLB based.
Oh, sorry, some mean field approximations.
So that was.
I know that you were talking about two-point probability function and then three-point probabilities with respect to being in the phase and being at the boundary.
Yeah. So that is related to. So just to comment. Is related to this part, rigorous bounds, and not directly to HLB based.
Okay, yeah, sorry. But the question is, you are using just standard two-point probability functions and the three.
And use 2 point.
Anyway,
3 point.
But the merit of the question is, you are not neglecting whether the positions or the points that you end up with are connected or not, right? And for this flow problem, maybe you have some cavities.
Yeah, you are talking about some type of information about the connectivity.
Yes, exactly.
Which we do not have from this. Okay, so that's certainly a missing point.
And the question is, do you think it is important to recover that, or do you think it's feasible to incorporate it in any way?
Well, in my experience, just to achieve this thing here, I spent many years on that.
Yeah.
I had a very complicated computation based on only for very specific type of microstructure with the Boolean spheres that can intersect and so on. And I spent days and days in computing that bounce. I would say it's not very efficient.
Yeah.
So I would, for the moment, I would not try that. I'm really investigating these things now.
Yeah, this is nice.
And so very recently, I have a PhD student working on this type of thing, but with a sphere's grain size distribution. So with very fine grains and very large grains, and that is in the context of internal erosion of soils, which are used in the dikes and levees and dams. So we can have a transport of the finest particles that leave the sample, and then your configuration of the grains will change and your permeability will change. And so he's doing this type of FFT simulations on samples which are generated using DEM, discrete element method. And then we move the grains, see how the permeability changes. And then we also do this. And very recently we found a way to, within 20% error, we could retrieve the permeability from very, very long computation. Whereas with the upper bounds I gave to you, previously, we were only maybe by a factor of 2 or 3 on the permeability, which is already good, but not 20%.
Yeah, I think there are some works by Torquato again in which they incorporate this information explicitly.
Yeah, certainly Torquato is the best.
Yeah, but I have never studied it in detail. And I do not know how difficult the computations are, but they are not certainly trivial. That is for sure.
And I would say it's very difficult to switch from one microstructure to another one because all these functions, they really depend on the microstructure. It's really hard to compute. So this bound things, it works well for mechanical properties, but for permeability.
Yeah, but it's the Linkman idea is really cool. Having the concept. Okay, so any other questions, comments, perhaps? People who are connected remotely, they of course can raise some questions, but they need to speak right away because we cannot see you, unfortunately, because I'm not educated enough to do proper screen share.
Il y a des gens du GEM là? On voit pas les noms. Ah, vous dormez.
That means no question. People who understand French and speak French, but unfortunately, I'm not one of them.
I think they can all speak English. No questions why they know me.
Yeah, okay. So thank you very much for your time. Thanks again, François, for this fantastic talk. Again, I enjoy it for the second time. And well, so if you would like to talk to François, he is here every day from 8:30 approximately till 7 p.m. next to my office. Unfortunately, I got now involved in some very entertaining things like doing some studies how civil engineering is organized at different cities.
Oh yeah.
I was unable to.
Lucky you.
Yeah, I was unable to interact with him more, unfortunately, and this won't change in the future.
So yeah, I think we could identify some common research projects and identify some funding to prepare for call for proposals together.
Yeah, and another option which I was made recently aware of is there are some options for co-tutel, sorry again for the pronunciation. And I spoke to the guy who was on the committee for math, but still he said that actually there were more stipends available than candidates. So this is also something which is interesting. And if I got it correctly, actually French side covers full 3 years of studies, which is very generous.
Really? Okay.
And in virtual phase, of course, we would be happy to host some of your students here, I guess. Okay, so sorry for that money-hungry speech at the end. But, okay, so thank you once more. I'll now stop.
Yeah. So I have brought some biscuits from Bretagne. Because I live by the sea, in Bretagne, and
It's and wine.
so